Let's say we have a relation that consists of 1, 1, 2, 2, and 3, 3. And we're asked to find the domain of this function. The first elements of each pair make up the domain. So that's 1, 2, and 3. We can put them into a list, which represents the domain, and it's just the elements 1, 2, and 3. But there's another way to do this visually as well, using a graphing program like Desmos.com. Go to Desmos. Type in the coordinate pairs. It makes a nice visual picture of your function. One way to find the domain is to figure out what x values those points are at. So if you do make a vertical line at those points, just click, and that x value of 2 is in the domain. Then we could do x equals 1. That's in the domain as well. And x equals 3. We're trying to find the x values of the points in question. That's how you find the domain. Now I'm going to show you the clever trick, how we can use technology to make this easier. What you do is you go to the wrench. You change the view. Okay, right now it's set to between like -1 and 8 for the x and -6 and 5 for the y. I want to dramatically change the y scale. So I can make it like 100. So from -100 to 100 is my new y scale. What this does is it flattens the image that you're looking at because the scale of the y is so big. The elements get moved more closer to the horizontal axis. And you just want to go even farther with that. Instead of going -100 to 100, let's go -1,000 to 1,000. Okay. Okay, now what we're starting to get is a picture of the domain. The domain is the x values of those points in question. It's the 1, the 2, and the 3. Now for some functions you might have to go really far with this, like -10,000 to 10,000. And now it's clear that those points are basically right on the axis, visually at least. And so then you put them into a little set, and that's your domain. I already did that. What's the rule that this function is following? I said that every function has to have a rule for how it processes inputs. And so for this function, we have our inputs on the left, outputs on the right, and if you put in a 1, apparently you get out a 1, because the input of 1 produces an output of 1. Now if you put in a 2, you get out a 2. And if you put in a 3, you get out a 3. The function doesn't really do anything to the inputs. Just lets them pass right on through, right? What's the rule for that? F of x equals, f of x equals x. So the inputs are x, and the outputs are x too, basically. We'll call it f of x. This function has a domain, which could be a lot bigger than just 1, 2, and 3. This is considered like a restricted domain for that rule, because many more inputs are possible. Let's see how many different inputs there could be. I'm going to fix my axes for a minute. I'm just going to go back to what it was. You could have 4, 4. You could have 5, 5, -1, -1. Even a fraction like 0.5, 0.5. If we draw all the points that fit that rule, we can just type the function right in, f of x equals x. Now you see all the points that would work with that rule. It's a continuum, so there's an infinite number of them actually. And if you're asked for the domain of the line there, then we got to give a lot more than just a list of a few points. We have to give a whole continuum, okay? So what I'm proposing is, the way we can do that is with this clever trick of skewing the axes. So go to the wrench here and type in negative 100 to 100. And you see what it does to the thing. Then let's go even farther. Negative 1,000 to 1,000. Okay? Let's go a little bit farther because they're not quite on the axis yet. Let's go negative 10,000 to 10,000. Okay, that right there is a picture of the domain of the entire line. It's the x values of all the points on the line. And now what you have to do is you have to state what the domain is here. That's a little bit more challenging than just listing a few x values. So let's see the different techniques we could use to do it. First off, we have to acknowledge that the line there goes on forever in both directions. Even though it's cut off on the graph here, that's just because I didn't have more of it graphed. If I was to zoom out, like in Desmos, on the x values, we could go to 100, we could go to 1,000, it's just going to keep going, okay, to the right and left forever. That concept in math, of course, is called infinity. So this line extends from x equals negative infinity to x equals infinity. Now, we have to have a mathematical way of saying that. Here's one way to say it. X can be any real number. Okay? If you remember the real numbers, we drew them one time, and we said the real numbers were just everywhere. And they go on in both directions forever. That's the real numbers. You can also write it like this. X could be between negative infinity and infinity. This is called algebraic notation. Okay, so algebraic notation is using the inequality signs. And there's another method that you have to be aware of as well. And it's going to be called interval notation. So interval notation is going to be done with either parentheses or sometimes with square brackets. In this case, the parentheses are the right ones to use because we always use parentheses with infinity. Okay, so just because we have parentheses and a comma between them does not mean that this is a coordinate pair of x and y. This is a totally different context and a totally different usage of the symbol. So what we actually want is the starting x of our interval and the x of the end of our interval. They're both x values. Okay, our start is going to be the one on the left. And our end is going to be the one on the right. So what we put in the parentheses then is negative infinity and infinity. These are all ways to express the domain of f of x equals x. In this case, there is no restriction on the domain like there was up here. Okay, we also have to be able to find the range. So in order to find the range, go back to your graph and let's just go back to the normal view for a minute. You can fix the window to something more reasonable. There's our original function, f of x equals x. We now want to compress it horizontally instead of vertically. Okay, so by compress it horizontally, I mean like if you were to push it more toward the y-axis. Go to the wrench for that. And in order to compress it horizontally, we just have to stretch the x-axis. And so go from negative 100 now to 100. it starts to look different. Then go from negative 1,000 to 1,000. And look how compressed it is horizontally. Okay, then go even farther. 10,000. What you're looking at there is a picture of what's called the range. These are the y values of all of the points in question. So we now have to express the range in a similar way that we did for the domain. The domain's all about x values. It's all about the horizontal values. Range is all about the vertical values. We have to acknowledge that the y values are going to go on forever toward the top and bottom. And that's heading toward a destination of y equals infinity for the top and y equals negative infinity for the bottom, because this is the y axis. And that's the x. So the range is all real numbers. That would be fine to say here. Or we could say that we could put it into a statement about y. Where are the y's allowed to be for this function? Between the lower start of the interval and the upper end of the interval. Y could be anything between negative infinity and infinity. You always start with the lower value when you're given the range. Okay, just like with x, you go from the negative side to the positive side when you state the interval. Same thing for the y. That's the negative y direction, that's the positive y direction. So you start from the lowest and go to the highest. We can put it into a interval as well. And that interval is simply going to be from negative infinity to infinity. This is going to be the start of our interval as far as y goes. And this is going to be the end of it. And y is all about elevation. Right? So you start at the lowest. That's what goes here. And then you go to the highest. In this case, there's no end to it in either direction, so it's totally unrestricted.